our international conference or seminar in inverse problems, and we are happy today to have Arnold from Merced, which will be talking about tunable high-resolution synthetic aperture imaging. So thanks a lot, Arnold, for coming virtually and giving a talk today.
Great. Thank you very much, Knut and Katja, for the invitation to speak. Everyone can hear me okay?
Mm-hmm.
Okay.
Yes.
So this is some recent work I've done in collaboration with my colleague, Ursula Sobka, who's also at UC Merced. And I'd like to acknowledge support from the Air Force and NSF for this research. This work has recently been published in the journal Radio Science, so in case you need that reference. So I'm going to discuss kind of a basic problem in synthetic aperture imaging. Suppose you have some sort of moving platform. Here I drew it as a plane on which there is a single transducer, which acts as both a source emitter and a detector. And in synthetic aperture imaging, what happens is as the platform moves along a flight path, which is defined by R of S. S is the so-called slow time, which is a time scale associated with the moving platform across some synthetic aperture, which is denoted here by lowercase a. At each, say, several points along this flight path, the transducer emits a signal, which then interacts with some imaging region. Here, say, suppose this Y0 is a target. And then that target scatters the wave, which is then recorded as echoes back. And so by concatenating this sequence of experiments where at each location along the flight path where you emit a source and record the echoes, move along the flight path, do it again. This is the so-called start-stop approximation for synthetic aperture radar. And the idea here is that the wave speed is much, much faster than the speed of the airplane, so that we can kind of, we need not take into account the velocity of the airplane in the modeling of the measurement. And so this is the imaging system I wish to talk about today. There's a couple coordinates. There's something, the distance along, say, the surface from the transducer to the imaging center of the imaging region is something I call capital R. The height, the elevation of the transducer is given by capital H. And this capital L is hypotenuse of this right triangle, which is the longest length scale in this problem. And we'll use that for some asymptotic results. So I'd like to introduce this data matrix. And so for each location on this flight path, which is R of S of n, which is denoted by this X of n, I'll use in my notation. So I have capital N locations where I take measurements. At each of those locations, I emit a signal and record its echoes over a discrete band of frequencies. So we're denoted by omega m. And so I'll introduce this matrix D, which is an m by n matrix, which contains the measurements from the sequence of experiments. And so the entry dmn of this matrix is the measurement at frequency omega m at location xn. And yet another piece of notation is just like each column of this matrix D is the corresponding frequency spectrum of echoes corresponding to spatial location xn. So then given this data matrix, I can introduce the inverse scattering problem, which is given this data matrix, recover the targets in the imaging region. And more precisely, with what resolution can we determine the location of these targets? And then in addition, are there other properties of the targets we may recover? For example, its material properties or something like that. So this is the general basic inverse scattering problem we seek to study in this lecture. And more specifically, I want to look at so-called sampling methods to solve this inverse problem. Sampling methods are very nice because they're quite simple. All you do is evaluate an explicit imaging function over some discretization of the imaging window or the imaging region that you're considering. and something like this imaging function peaks at target locations if it works well. So this is very nice. There's no optimization. There's no any other kind of things that we worry about. It's simply the evaluation of some function over a region. Of course, the challenge is the design of this function to work for these problems. So some famous examples of sampling methods, and these are just some of them. Kirchhoff migration, which is kind of the typical thing that one does in synthetic aperture radar imaging. Music, which stands for multiple signal classification, which is the so-called signal subspace method. There's the linear sampling method. Pardon me if I get these references wrong, but I typically associate this to Coulton and Kirsch in '96. But Cocconi, Coulton, and Monk have really developed this theory and applications of it. There's the factorization by Kirsch in '98. And then there's something called coherent interferometric imaging, which was introduced by Borchea, Papanikolaou, and Sonka in 2005. And then Garnier and Solna modified SINT for the synthetic aperture radar imaging problems in 2008. A particularly useful reference for me as I was kind of evaluating and surveying these sampling methods was work by Margaret Cheney in 2001, where she established an equivalence between music and the factorization method for the special case of point-like scatterers. And this got me thinking about that there's something kind of elementary going on with all of these sampling methods, and that's kind of what I'm hoping to be able to discuss today. So the overview of what I'd like to discuss is to determine elementary features in these sampling methods. And by doing so, the hope is that once you know what the elementary, say, mechanisms, mathematical mechanisms going on with these sampling methods, then once those are understood, we can know how to kind of repurpose things or modify things for different types of applications. And so the one simplification I'll make throughout this talk is I'm only going to consider small point-like targets. So the targets are smaller than the wavelength, the typical wavelength used to illuminate the region. And so what I'll first do is give an overview of a modification that Chrysula and I made to the music method to achieve quantitative images of point targets for these synthetic aperture radar problems. And then by doing that, we can kind of reevaluate what we've done and identify that there's this really very simple elementary feature in music, which is the reason why it produces such high resolution images. And then after identifying this, you'll see that it's just a simple transformation of the data that we could apply to any imaging method. And so what we'll do after that is modify Kirchhoff migration, which is very useful for problems where you have low signal to noise ratios, and then also for coherent interferometric imaging for random medium problems, respectively. And a key to this modification is the introduction of a user-defined parameter, which you can adjust to basically achieve whatever resolution you'd like. Okay, so just a little bit of the mathematics of scattering that we'll use in this talk. So we consider time harmonic scalar wave propagation governed by Helmholtz's equation. And we'll make extensive use of the fundamental solution, which I denote here G sub m, where m is the discrete frequency being used and c is the wave number, or excuse me, wave speed. And we'll work in 3 dimensions, so we'll use only this fundamental solution. And so when we have a target centered at some location y0, and it's small compared to the wavelengths that we're using in this problem, we can approximate it as a point-like target. And under the first-born approximation, the scattered field by this point target is a spherical wave that radiates away from the target location y0 that is modified in amplitude by the wave field incident on that point and something called the reflectivity, which is typically a complex scalar for a point target. So the scattered field produced by a point target is a secondary spherical wave modified by something called the reflectivity, which is related to the scattering amplitude of the target. Okay, so now what I'll do is use this model for the scattered field and develop a model for the measurement matrix that I introduced at the beginning. So at a fixed frequency omega m at location xn, we use as the source emitted by the transducer another spherical wave. And so the incident field then is just the fundamental solution radiating from the transducer location xn. That then is incident on the point target y0, and then that secondary spherical wave that radiates from y0 is scattered field. So this is the scattered field. And then when we substitute in our expression for the fundamental solution, we find that the dmn entry of the data matrix is given by over here, rho 0, this complex exponential, and this amplitude. So you can see why we're using these point targets, because we get this explicit model for the data matrix. Okay, so now what I'd like to do is introduce our modification to music that we applied to these problems. So it's well known, music is a well-known imaging method. It produces very high resolution images. But as far as I did, there was always missing some sort of resolution analysis associated to it. My experience with the literature has been when it works really well. When it doesn't, it kind of doesn't, and it's almost binary in its use. And so that was one thing that we thought was an open issue. And then with regards to synthetic aperture imaging, the conventional wisdom was that music didn't really apply to these multi-frequency synthetic aperture measurements. But a key work in 2017 by Griesmeyer and Schneidecke, I think I said that right. Well, I said that poorly, but hopefully not too poorly. They introduced a modification to music for this problem. And then later on, after seeing that work, we recently analyzed this method and made some very simple modifications, which then allowed us to produce a quantitative imaging method with tunable high resolution. And so I'll go through it briefly what we did. So the method really is just the procedure that we introduced has these 4 steps. So the first thing is to pre-process the measurements using something called the Prony method, which I'll describe in just a second. So for each spatial, excuse me. When you do this to the entire data matrix, you obtain a m times n divided by 2 squared block diagonal matrix. And then you compute the singular value decomposition for each diagonal block. And then given those singular value decompositions, you can construct an explicit imaging functional. Here I denote it by f sub epsilon of y, which can now be evaluated at all the search points in the imaging region, and it will take on a peak value at the target location. And also its peak value, its magnitude will be exactly equal to the absolute value of the reflectivity. So this is what we mean by quantitative. We get not only the target location, but the modulus of the reflectivity. If we then wish to recover the complex reflectivity, we can then use our result of y0 from step 3 and evaluate another imaging functional. Here I call it r sub epsilon of y. And that actually allows us to recover the complex reflectivity. So now I'll go through each of these steps in some detail. Okay, so here I'll work with the nth column of the data matrix, which I'll remind you corresponds to the frequency spectrum of the echoes received at spatial location xn. So this corresponds to the frequencies of the echoes received at a fixed location. And so given this vector dn, the Prony method produces an m/2 by m/2 matrix, which I'll call capital Dn. So it's easier to see the action than to define it. So if I have this vector dn, the components or the elements of which sweep through the frequencies at n, then the first column of the Prony matrix is just the first half of this vector. And then you see this sort of circulant sort of definition of the next vectors. So you could just take the circulant extension of this vector, and then you take the top quadrant of that, and that is the Prony matrix. So if you look at the next one, it starts at 2 and goes down, and then so on and so on. So that is literally the Prony method. So you just kind of circulantly modify this vector here, and then kind of chop off the first quadrant of that, and you obtain this dn matrix. So then when we apply the Prony method to our data, a model for the measurements given by this expression here, we find that dn is given by this matrix. So we can write everything out explicitly. Here I introduce the notation tau n, which is just the 2 times the travel time from the source location to the target location. Okay, and now the key observation given this matrix dn is the following, that when we have equispace frequencies, which is usually what we work with when we use with, say, discrete Fourier transform, with some constant sampling rate denoted by delta omega, then you can write the dn that I wrote in this previous slide as the following outer product. So there's a value, constant value of capital M, the number of frequencies, times the modulus of the reflectivity and this amplitude that comes from the fundamental solution. And then you have this vector, which I'll call U1, which is just I omega 1 tau n down to I omega m over 2 times tau n. It has this normalization factor here and this complex exponential that comes from the argument of the reflectivity, which is written here. And then the other vector V1, Hermitian or conjugate transpose, which has this structure here. So this kind of circulant structure in the Prony matrix can be rewritten as this rank 1 matrix, this explicit outer product. The nice thing about now having this expression is that when there's no noise in the problem, we now have the singular value decomposition of this dn matrix. It's simply given by this rho 1, which is, again, this constant real positive number we get over here, and U1 times V1 conjugate transpose. And for the case of no noise, we know that all other singular values are 0 identically. This allows us to then think when there is noise, but the signal is sufficiently strong, then the first singular value will be much larger than the others. So we have this sort of asymptotic relationship. And so in that case, we could then construct the following imaging functional using this. So suppose we've computed the singular value decomposition of the Prony matrix dn for each column of the data matrix. And in doing so, we observe that there's only one significant singular value. And notice that that would be true for each of the n's because of the construction of this Prony matrix. Then the next thing we do is we introduce a pseudo inverse for the diagonal matrix of singular values. So I yank out 1 over sigma 1, and I introduce an epsilon into this, which is like a threshold value for the pseudo inverse. But it's a user-defined parameter. And so then so for any search point in the imaging region denoted by y, we would simply compute this vector a sub n, which has this amplitude term, and this corresponds to the analog of the singular vector u corresponding to the data matrix, but it's evaluated at y instead of at the target location. And then we evaluate the following function, which is just the sum over all of the locations along the flight path of this kind of inner product, where we now put in this pseudo inverse into the function. Okay, so this is this explicit construction of this imaging function. Now, suppose we have a target location y0. In addition to that vector an, I'm going to introduce another vector bn, and this mimics the right singular vectors in the singular value decomposition of the Prony matrix, but instead it's evaluated at the search point. And then I'll evaluate this function r at y which just has this, B conjugate transpose times the right singular vector, the pseudo inverse to the left singular vectors in a product with A. Okay, so you just simply construct these two functions, evaluate them throughout the imaging region at all the points you care about, and then you evaluate and plot their reciprocals. So if you evaluate and plot the reciprocal of F, you will then determine the location of the targets. And then using those locations, you could then evaluate 1 over the R function to determine the complex reflectivities. And notice each of these has this user-defined epsilon. It need not be the same for these two steps. You can choose them individually, and you can adjust them to tune the resolution to whatever your needs are. So using this modification to music, we were able to establish the following results. I'll just summarize them. In the limit where this L, that length scale, is the largest length scale in the problem, and the asymptotic limit is that gets large, we find that the range resolution that we get, so that this plotting 1 over F yields a peak that is centered at the actual target location. And its range resolution, the width of this peak, roughly speaking, scales like the square root of epsilon times C over B times L over R. So a C over B is what we typically see in Kirchhoff migration imaging resolution. And its cross range resolution, which is the parallel to the flight path, will be square root of epsilon C over B times L over A. And then here you see the aperture interacting with the distance in the usual way. And then on the exact target location, we recover exactly the complex reflectivity. And then if you randomly perturb the travel times in the data, we find that the images formed through the evaluation of 1 over F are statistically stable when the variance is sufficiently small compared to the user-defined epsilon. The key here is that if you had an estimate for the variance of the uncertainty in the travel time, then you could actually choose epsilon in a way such that this asymptotic result is true and attain statistical stability in your image reconstruction. And then keep in mind, for all 4 of these results, the parameter epsilon is free to be tuned as you see fit. Okay, so this is an example image when we apply this method. So here is the resulting image of 1 over F, this 1 over F function, for this situation where the distance from the transducer to the imaging window is about 8 kilometers. It's a 622 megahertz bandwidth, speed of light in air, and the aperture is about 0.13 kilometers. There's some noise, so we have 44 dB signal to noise ratio. In this case, the reflectivity has magnitude 3.4. So I call your attention to the color bar, that the peak here, which is centered about I plotted this function that's centered about the target location, takes its peak at the target location, and its peak value is the modulus 3.4. And for this case, I used epsilon 10 to the minus 8. So it's quite small. I've also scaled the range and cross range, the X and Y axes, by the central wave number. So these units are more or less in terms of wavelength. You can think about 6 times the distance over the wavelength. And so you see that we obtain a resolution for this target, this individual target, that's well with fractions of a wavelength, very small fractions of a wavelength. In these 2 panels here, I plot the cross range and range slices of this image, just to show it does peak at the value 3.4 and that its width is quite narrow. To test the resolution estimates, what we did was we varied all of these parameters we had in the problem, evaluated the function numerically estimated its full width half max, and then use those as estimates for, or use those as image resolution results. And I plot those here. So this top left panel shows these image resolutions, these full width half max computed from the numerical evaluation of a function as a function of epsilon over several decades. And as reference, I give the square root of epsilon as a black dashed line, and you see both follow this behavior exactly. Here, I vary the bandwidth so that this ratio C over B, which plays a role in both of the imaging resolution estimates. And you see both range and cross range. The numerical results match this behavior. In the lower left, we're changing the aperture such that the ratio L over A changes. And to see the behavior of the imaging resolution, here we see that the range is relatively unaffected, but the cross range is very affected, consistent with our imaging resolution estimates. And then this L over R ratio, we varied and showed that, again, the opposite is that the cross range is relatively unchanged with this parameter, but the range follows kind of this order 1 behavior in this ratio. So these numerical simulations validate our theoretical image resolution estimate. Then what we do is we evaluate this 1 over R to see if we can recover the complex reflectivity. And these are the results of plotting 1 over R as a function of the cross range and range X and Y respectively. The blue curves are the real part of the result, and the red curves are the imaginary part of the result. And for this case, we use the reflectivity that is purely imaginary. So if you see at the target location, the real part is identically 0, and the imaginary part takes on the value indicated by the X, which is the true value of 3.4 times I. For this case, it was the same setup. It's actually the same exact data I used for the previous results. Here I change epsilon to 10 to the minus 10. And the numerical recovery at the target location we recover from the previous slide, we get something that's 3.39, which is very close. I, and then 10 to the minus 3. The noise in the problem does kind of, the error in this recovery is due to the noise introduced into the problem, the measurement noise. Excuse me. So this works well. I should just say it's not effective to use this R function to image the target because it actually doesn't necessarily peak at the target location. So we only make use of it kind of locally to where the 1 over F kind of gives us guidance as to where to evaluate. Okay, so then the key here is like, why does this method work? What's going on? And this is something that we are keenly interested in understanding. And so if you work through the algebra for this function F that we introduced, you can basically write it this way. So in music, we often speak of projecting vectors onto the signal subspace or the noise subspace, which are orthogonal complements to one another, which is basically, and then we get a basis for these subspaces using the singular value decomposition. So I wanted to write what we were doing in this framework. And so effectively what you're doing, so we have this test vector, here I normalize it, A hat, right? That's evaluated at each of the sample points that we're considering. And we consider the projection of that vector onto the signal subspace and also onto the noise subspace. If there is a component of this vector in the noise subspace, we amplify it by 1 over epsilon. When it is exactly in the signal subspace, this first term identically goes to 0, and we're left with this, this result. And if you just write out, for the case of a single target, we have those expressions from before. We have the singular value decomposition analytically, so we can write down explicitly what these projections are. And then if you substitute this all in and just do a little bit of algebra, you obtain this, this result that 1 over f looks like epsilon over the sum over n of 1 minus the quantity 1 minus epsilon times this quadratic. Okay, and so just by wanting to write down the function in terms of these projections, you can obtain this result in elementary linear algebra. So now we look at the subspace projection. Oh, and by the way, this inner product really kind of corresponds to the signal subspace projection, right? And these ones correspond to the complements, right, from the noise subspace. So in our analysis, for the resolution analysis results I summarized earlier, it basically boils down to the following, which is if I have this function, which is given by this quadratic, it more or less looks like 1 minus something squared, where that something is centered about the target location. So you get this quadratic looking function locally. And this result shows that if we just use f as a function, we would get an image that would peak at the target location. Okay, and then the width of this peak would then be controlled by beta. And then what happens in music is you actually compute something like a Möbius transformation of this function. So I'll call this G, which is just epsilon over 1 minus epsilon times f. And if you work out, it's just an elementary calculus exercise, you then see that you scale the previous result by 1 over epsilon. So this is why music is achieving this high resolution. It's just by this reciprocal sort of evaluation. What we did was we introduced this epsilon. So instead of the function becoming singular, it's now regularized. It's a bounded, continuous, nice differentiable function. So we can do all this just using elementary calculus. And so just through this rational transformation of this function f, you can then get the scaling of the resolution by the square root of epsilon. And that's really the elementary mechanism in music that's kind of making it have such a high resolution. And then now we see what this tuning parameter we introduced is actually doing to the resolution. It's just a simple sort of transformation from F to G. Now that we've kind of figured this out, we now have this method that can compute quantitative images of point targets. We now have this epsilon value we've introduced, which allows us to tune the resolution. This has been useful because sometimes you want to evaluate, say, a large imaging window with a relatively coarse grid. When you do that, you can tune epsilon to be not so small such that its support can be captured by the grid that you're using. And then as you kind of window around and you see where targets are, you can increase the resolution, decrease epsilon, and tune these things in a dynamic way as you look around and identify targets. It is stable to relatively to random perturbations of the travel time. They have to be bounded, and the epsilon has to capture this. So it's not widely applicable, but it does work. The main limitation, and this is a limitation inherent with subspace methods, is you need to be able to distinguish reliably between signal and noise, which basically means, right, there is an elementary or a fundamental step in what we did, which is that we identify singular values in the singular value decompositions that correspond to signals, and we kind of ignore everything else. As noise increases, we're not going to be able to do that so reliably. And so that's a key limitation here. I have learned that, like for many radar problems, they have kind of rather low signal to noise ratios, and that would then render this method not so useful. So it's for that reason, this practical idea that there's a lot of noise in these measurements that we thought to do something else. So I want to return to this Möbius transformation, right? And I said this before, but if you had any function that kind of has this quadratic behavior around the target location, then you could always pull off this kind of reciprocal, rational transformation of this function and obtain a better resolution, a nicer imaging function. And there's nothing special about f. We just needed to have this quadratic behavior for this to work. And so if we used another imaging function, not the signal subspace projection, but rather something else that could be used for low signal to noise ratio problems, we could then compute this transformation of that imaging function and presumably get tunable high resolution, just as we did with music. And so our idea now is to apply this to Kirchhoff migration. Kirchhoff migration is known to work for low signal to noise ratio problems. And so just to describe, or just to write down exactly what Kirchhoff migration is you take the data and you basically back propagate it to the search point y. And so when you substitute in our expression for the data matrix and take the sum, this is precisely the Kirchhoff migration imaging function. And it's well known, and I believe it is the typical method used in radar, and that it's known to be stable to large measurement noise, because more or less from a signal processing point of view, you're computing a matched filter. So it has certain optimal qualities with respect to measurement noise. So we introduced, given what we've discovered with this music algorithm, we now do the following. Suppose we normalize, this should be the absolute value of this imaging function by its peak value. Presumably that's where the target is, but we just normalize it so the peak value is 1. Then we take that result, and I'll call that I hat, and I'll simply evaluate this Möbius transformation and call that I epsilon. And so the expectation is that we could then use epsilon to tune the resolution of Kirchhoff migration. And so the proposal now is to use this new imaging function to get high resolution imaging for low signal to noise ratio problems. And this is just one example. So this is the result for 1 point target. I've plotted it in a dB scale, which is log base 10. And this is the standard Kirchhoff migration result. You get something that looks like a sinc function in range and cross range. And when you apply this Möbius transformation to the normalized version of this image, you get this incredibly sharp resolution. Here I chose epsilon to be 10 to the minus 4. And in this case, the SNR is it's much smaller than previously that I was using for music. It's around 15 dB, but you can drive this even lower, and it still works this way. And we did the same sort of numerical evaluation. We took this noisy data, and then we found the full width half max and see if it scaled with square root of epsilon, and both range and cross range do. So it works precisely as we had hoped that it would, given what we understood from our modification of music. And so then what happens if you have multiple targets? Well, if we take the original Kirchhoff migration image, you see that the pluses indicate the true locations of the targets. There are 3. And what we then do is say, oh, okay, so there's got to be something around here. I'm going to create a window and then basically just take the data, the reconstructed image, renormalize that to have a peak of 1 within just these values, because these peaks may have different values. Well, actually, sorry, I'm ahead of myself. If I just take this image, normalize it so its peak value is 1, and then do this Möbius transformation with epsilon equal 10 to the minus 4, I get this result. So again, you see pretty sharp localization of the targets. The key here, though, is I was getting ahead of myself, is that these peaks are not all the same values. So when you normalize this Kirchhoff image by its peak value, each of the targets may not exactly be 1. So you see yellow is the brightest, or is the tallest. That's the one where it does normalize. But these other 2 targets are not as tall as the other 2. Here, and this is a pretty low SNR situation, right? 4 dB. We're getting it pretty close to like equal noise and signal amounts. So then what we do is, okay, I did this modified Kirchhoff migration and I got this. Now I can take different windows of the original data, given this result, normalize within that subset of Kirchhoff data, normalize that to its peak value, then apply this reciprocal in this local window. And when I do that for windows about each of these locations, I get the following results. So again, you get incredibly sharp images. You notice this is like fractions of a wavelength. And so by applying this Möbius transformation to the Kirchhoff image in these local windows, we retain this incredibly sharp recovery of the target. It's also interesting to note that if you look, the targets predicted are shifted a little bit. I mean, again, this is within a wavelength or so, with the SNR again being around 4 dB. So this is something we might not have necessarily been able to observe in Kirchhoff migration, but what happens is, because you get such high resolution of the target locations with this reciprocal trick, you then are able to see that the noise in Kirchhoff migration does shift the predicted target location. And so we're working on computing exactly what this shift is, but it's also, at least from numerical simulation observations, on the order of a wavelength or smaller. So it's not a huge shift, but it does shift. Okay, now we thought it works for Kirchhoff migration. Does it work for other stuff? So now we thought about imaging with waves in random media. The challenge here is when waves propagate in a complex medium for which the material properties are uncertain, it's well known that the Kirchhoff migration imaging method for targets in a complex medium becomes statistically unstable, meaning that reconstructions for individual realizations of the random medium are different. They dance around. I'll show you an example. To address the statistical instability of Kirchhoff migration, Borchea, Papanicolaou, and Zonka in 2005 introduced something called coherent interferometric imaging for active array imaging. And the idea here is, rather than think about inner products with the data itself, you work with correlations of the data, because that's a much more statistically stable object to work with. Garnier and Solna extended SINT for synthetic aperture imaging. And the key here is that SINT is now limited by something called the decoherence frequency and decoherence length. So what happens when you have multiple scattering in a random medium, that basically messes things up. And so all of your spatial and frequency data are not, a portion of that can be so corrupted by the multiple scattering that it doesn't carry any information content about the target anymore. And so in SINT, what you do is you work hard to identify which subintervals of frequencies and spatial locations do carry information content and use only those. Hopefully that makes sense. But the idea is, suppose SINT works, the conventional wisdom is that you have to give up resolution to get statistical stability, right? Because you now only can use, say, some subset of the frequency band, you cannot attain the same resolution you would in a homogeneous medium using Kirchhoff migration, because you basically have to throw away some of the resources in the imaging system. And so the conventional wisdom is SINT works, it's statistically stable, but you lose resolution, right? So there's a trade-off between resolution and statistical stability. And so the idea that Krasul and I had is, well, can we get it back just by doing this reciprocal transformation? And so here are some results. I don't have any theory about it, but we just computed some results. So here's a picture show. So I'll show two different realizations. So this is the SINT image that gets reconstructed. This is when you do the Möbius transformation. I forget what epsilon is for this case, but you see the image sharpness is dramatic. We also applied the same music algorithm that I explained earlier. It too also works, but the scent is better. The epsilon scent, or this rational transformation of scent, works better than the music. And here you see the Kirchhoff migration. You see that it's very, there's lots of imaging artifacts, and that is one of the visual manifestations of its statistical instability. So if you look at these four and think about the comparison, it looks like this one wins in terms of being most resolved. Here's just another resolution. So it's just a different realization of the same random medium. Scent gives a nice stable image that's centered at the target location. You simply normalize it and do this rational transformation, and you get this higher resolution image of the target. Epsilon music works as well. Oh, you can see it shift a little bit in range, but not as good as epsilon scent, which is explicitly designed for this random medium problem, so it's going to be better. And Kirchhoff, you could argue, is okay, but if you allow me to just flip back and forth, and if you keep your eyes on the lower right image, you'll see that, right, the predicted target location dances around. There's lots of artifacts. It's not going to be a reliable way of identifying targets. Whereas if I call your attention to the upper right, these are two different realizations. The peak dances a little bit. Again, I would argue it's really tightly bound, although I don't have an estimate for this. It's an open question. But simply just by basically taking the reciprocal of scent, you get a much higher resolution image. Okay, let me wrap up and just say, by reviewing the quantitative subspace imaging method for synthetic aperture imaging, we identified this really very basic elementary mechanism that gives us tunably high resolution. And this mechanism is just really taking the reciprocal of the normalized image that you compute from before. You have this tuning parameter epsilon that just kind of basically regularizes that function. In the Möbius transformation is quite general. It can be applied to any normalized image regardless of the method used. And so far, we've been able to apply this to both Kirchhoff migration and scent. And that allows us to look at problems with low SNR or imaging in random media, respectively. So thank you very, very much for the opportunity to present this, and I'm all done.
Thanks so much, Arnold, for a very interesting talk. Some very nice concepts here. So, so the floor is open for questions. So please feel free to unmute yourself and ask questions.
Hi, here is Mikhail Gelman. I have a question. If I understand this correctly, this deals with super resolution. And I wonder if you have examples where you have more than one point scatterer separated by the distance less than the resolution. Will this method resolve two such scatterers? Thank you.
Yeah, this is an excellent question. So the honest answer is I do not know. It's something I'm trying to look at right now. So let me just make sure I get the question. So if you have 2 point targets that are kind of within the resolution of Kirchhoff migration, does this reciprocal thing, did it kind of disentangle those two targets?
Yes, this is what I mean. Yes.
Yes. Yeah, so again, so the honest answer, and then I'll give you my political answer. The honest answer is I don't know. I don't have any results. I have some numerical results, which basically show that sometimes yes and sometimes no. But nothing systematic that I can say. The general idea, let me say this, the safest thing I can say is when you can distinguish individual targets with Kirchhoff migration, then this will work. I feel confident saying that. It's open whether or not, the question you ask is open. It's something I'd like to be able to figure out, but I haven't figured out yet. So hopefully my
Okay,
honesty
thank you. Thank you.
can compensate for my lack of an answer.
So any other questions for Arnold? So I was wondering, sort of, a little bit in similar way, if you consider extended targets, have you considered extended targets?
No, I've been wanting to. So I wonder. So if we apply this to linear sampling, for example, this I'm giving this away, right? But this is my hypothesis: is that maybe you usually get something that kind of concentrates on the singular support of the object. Does it kind of sharpen that? You know, I don't know yet. It's on my list of things to do, and I haven't tried it. But it's a really good question. I don't know yet. If you guys want to help, I'll take the help.
Yeah, no, I think it's a very interesting results here. So very much worthwhile to consider further these things. So I was wondering, for when you construct the image, you sort of look only use the block diagonal, don't you?
Yes.
Is there information in the off diagonals that you perhaps could help you?
Yeah. Okay. So that's also, I can tell you, thought about these problems a lot. That's actually the thing I didn't like about this music method, right? Which is, notice that the resolutions compared to Kirchhoff are a little different, right? See, here you have the C over B, but you have the C over B in cross range too. And that's the result of basically not coherently summing over space. It's that block diagonal. We tried a method that kind of tried to do this, but it wasn't exact in terms of the music construction. I don't know if that makes sense. So there's this idea of music being exact for certain factorizations in the matrix, and it didn't work for that. So, and that's why, for example, sorry, this is a little esoteric, but if you look at the music, right, this cross range is not as good as, say, the synth, right? And it's because we're incoherently summing the X's. So we don't gain for that. But then in the music case, we thought, oh, well, I'll just crank epsilon down and, you know, to machine precision, and then who cares? But you see in this case, that's why this is so kind of with the word prolate compared to the synth one. It's because you're not combining spatial information. You treat it kind of, as you say, only diagonally, right? We don't consider off diagonal things. It would presumably be better if you did, but we just didn't. I don't know how to. Didn't know how to make that work in the music framework. Yeah, but that's a subtle thing, right? You see the estimates and they don't feel right. But it's precisely because of this block diagonal kind of restriction that we did.
Am I allowed to ask another question?
Go ahead.
So if you show again that slide that says summary of theoretical results, probably something like this. Yeah. So we see that the resolution, the expressions for the resolution, they depend on epsilon. And
yes.
Again, if I understand it correctly, epsilon is somehow related to the level of noise. So the resolution depends on the level of noise. Do you have certain any kind of interpretation? Is how we create resolution for noise and other similar situations when this is the case? Thank you.
Yeah, okay. No, good question. So recall this is where we introduce the epsilon. So we take this is the pseudo inverse of the sigma matrix in the singular value decomposition. So it is in a certain sense set by the noise because we need to know after which singular value is it noise. But once we do this, we artificially drop it, the singular values down to the epsilon. Which sounds kind of magical. What the manifestation of when you have more noise, but you can reliably distinguish the signal to the noise, is when you try to recover rho, you get from this R function, excuse me, then you don't get the quantitative, the error is in the quantitative information. But because you kind of, if you know where the noise starts in this singular value spectrum, you cut it off and you basically threshold it to whatever value you would like. So from just the image of the peak, it's not affected by noise explicitly. It's through the implicit decision of where you cut off the singular value spectrum. It's a slightly subtle point. But that's why if you can't distinguish between the signal and the noise and you cut wrong, then it kind of catastrophically doesn't work.
Okay, thank you. This is very interesting. Yeah, thank you for your.
Thank you. Thanks for the question.
So again, a question a little bit in the similar vein, if I could. So let's say that is R or epsilon more sensitive to noise than F, such that you can use a different epsilon, or is it sort of same? Would you?
Yeah, so that's right. You could do that. So right, this function, right? It doesn't peak at the location, so it doesn't have this kind of monotonic, and you can see it's not a symmetric positive definite sort of thing, right? Whereas this one is designed to be, right, symmetric positive definite. So it doesn't have this kind of quadratic behavior. So you could, if you look back at the plots, you could adjust epsilon so that it kind of smoothly, at least in the neighborhood of the target, varies in that region, and use that as an estimate, or some say mean value or something like that. It wouldn't be a good idea unless you were very, very confident in the recovered target location to drive epsilon very small for this case, something like that. But you see, I'm sorry, what did I use for epsilon? 10 to the minus 10. So I actually drove it quite small. But if you make it bigger, then it smooths it out. Again, it's not good for imaging the location, but if you wanted to estimate this value, you would get a much smoother function about that, about the rho values. But yes, with regard to Mikhail's question, this part of the recovery is much more sensitive to noise.
Great. So any other questions? I think we had already some. So unless there are any other questions, let's thank Arnold again for a very interesting talk. Nice techniques, and thank you for coming and giving the talk, and also to your co-author Chris Urla.